It's been in space for less than a year, but it's already changed the way we see the universe. The first images from the James Webb Space Telescope, JWST, launched into deep space on December 25, 2021, have left professionals and hobbyists in awe. The most powerful space telescope ever, far superior to its scientific predecessor Hubble, is expected to elevate our understanding of the cosmos to unfathomable realms in the near future. This $10 billion instrument, specially designed for infrared astronomy, will allow us to see the first light formations that formed after the Big Bang in the so-called Dark Ages. However, some of the data transmitted by Webb-to-ground research stations also raises important questions, suggesting that some of the observations may be at odds with the Big Bang theory. Could this mean we should consider a complete rebirth of our cosmic home? To understand why some observations from the James Webb Telescope are shaking up the theory of how the universe originated, let's first look again at the Big Bang itself. According to the standard cosmological model, the Big Bang refers to the process that led to the evolution of the universe about 13.8 billion years ago. Although the term Big Bang sounds extremely belligerent, it does not mean a gigantic explosion in existing space. Rather, space itself, along with matter and time, emerged from a primordial singularity. In astronomy, a singularity describes places where the gravitational force is so strong that the curvature of space-time breaks down or, more simply, becomes infinite. But how is it possible to reconstruct the origin of the cosmos today? The universe provides natural help here, for it is not a rigid, immutable building, but one that is ever-expanding. Looking back at the expansion of the universe, we reach a point where the density of energy and matter becomes infinite. The best evidence for the Big Bang theory is the detection of the cosmic microwave background radiation. After the birth of the cosmos, matter and radiation were initially in thermal equilibrium. As the universe expanded, both temperature and density decreased. About 380,000 years after the Big Bang, the temperature dropped to about 4,941 degrees Fahrenheit, allowing electrically neutral hydrogen to form. Without free electrons and protons participating in recombination, radiation could no longer interact with matter, making space transparent. The near-isotropic microwave background radiation that still fills the universe is from this era. The exact processes and the time of the formation of the first stars and galaxies are still unclear, a key question for which the James Webb Telescope is designed to answer. Although the Big Bang theory is the widely accepted leading explanation for the creation of the universe, historical precedents show that experts can be drastically wrong. For example, the geocentric worldview was once deeply embedded in the minds of our ancestors. Also, the Big Bang theory, which describes not the actual event of the Big Bang, but the early cosmos shortly after its formation, is now being questioned. Our current physics cannot describe the real Big Bang, let alone the time before it. Among those who question the current doctrine is Alison Kirkpatrick, an astronomer from the University of Kansas. He worries about Webb's latest revelations and points out that the discovery of surprisingly small, uniform, and ancient galaxies contradicts the predictions of the Big Bang theory. This theory assumes that galaxies and other objects in expanding space do not appear smaller as distance increases, but become even larger after a certain point. However, Webb's images show that similar structures are getting smaller and smaller, even those gravitationally bound star clusters that clearly exceed our own Milky Way in mass and luminosity. This unexpected fact leads some scientists to propose a revolutionary thesis. The universe is not expanding and the redshift is not proportional to distance. Albert Einstein believed in a static universe and introduced the cosmological constant to fit this assumption into his equations. This step, which he later rejected and called the greatest stupidity of his life. Although Edwin Hubble introduced the expanding cosmos in 1929, some scientists still believe that the idea of an expanding universe is a big hoax. Eric Lerner and Ricardo Scarpa concluded from the Hubble images that the redshifts were consistent with a non-expanding cosmos and assumed that the Webb images supported their beliefs. They expected images of almost confused galaxies with clear signs of mergers and collisions, but the reality presented a different picture. ancient star clusters look strikingly unified structures, just like their younger counterparts. Webb's observations show that ancient galaxies are 10 times smoother in shape than previously predicted. Studying distant galaxies is like optical time travel, because their light traveled billions of years before reaching us. According to the Big Bang Theory, the most distant and oldest galaxies visible in Webb's images formed approximately 400 to 500 million years after the creation of the universe. However, some of these formations apparently have stellar populations over billions of years old. Since nothing could have been born before the Big Bang, the existence of these galaxies challenges the Big Bang Theory. Papers published so far show that the Big Bang Theory has 16 false predictions and only one correct one. For example, predictions of the abundances of helium and lithium differ by a factor of 2 and 20, while only the abundance of the hydrogen isotope deuterium is correct. In addition to these problems, there are structures in the universe too large to have formed after the Big Bang, wrong predictions about the density of matter, and unexplained asymmetries in the cosmic microwave background. These problems question the foundations of the Big Bang Theory. However, the discussion of these contradictions receives little attention in the mainstream media. Opponents of the Big Bang feel marginalized, often labeled as ignorant or incompetent by the scientific community, and their work is rarely funded. The other camp, however, maintains that Webb's records still await a full review. Although some preliminary data indicate a very high age for certain structures, controlled analysis is needed to confirm these assumptions. The debate about the Big Bang Theory and its impact on the understanding of the cosmos continues to provoke deep thought and keen attention among scientists and enthusiasts. The theory centers around a single event 13.8 billion years ago, when space, time, and matter emerged from an infinitesimal point known as a singularity. Although this concept is widely accepted, it faces significant challenges and skepticism. One point of contention concerns the interpretation of observational data, especially for advanced telescopes like JWST.
Launched to probe deeper space and time, JWST's initial findings both intrigued and puzzled astronomers. The discovery of ancient galaxies that appear unexpectedly unified sets up models of galaxy formation and evolution. Conventional models predict that as galaxies age and gravitationally interact, they should become more disordered and irregular. But JWST reveals ancient galaxies that retain a surprising uniformity reminiscent of modern spiral and disk galaxies. This finding raises fundamental questions about the mechanisms that drive galaxy formation over cosmic eons. Furthermore, age estimates for some ancient galaxies based on their stellar populations are another puzzle. Stars in some galaxies are over 1 billion years old, defying conventional timescales derived from the Big Bang Theory. This contradiction challenges the notion that nothing could have existed before the Big Bang. Another controversial area is the interpretation of cosmic expansion and redshift. The Big Bang Theory is based on the idea of a constantly expanding universe, where galaxies are moving away from each other at a rate proportional to their distance. This expansion manifests itself as a redshift in the light emitted by distant galaxies. However, some alternative theories indicate that the redshift may not be due to the cosmic expansion alone, but may also be affected by other factors, such as the intrinsic properties of galaxies or variations in the speed of light across cosmological distances. These ideas challenge the fundamental assumptions of the Big Bang Theory and prompt a re-evaluation of how we interpret observational data from telescopes such as JWST. Critics of the Big Bang Theory also point to inconsistencies in the abundance of elements such as helium and lithium, suggesting that our current understanding of the early universe may be flawed. Although the theory explained many observed phenomena, its predictive power appears to be limited in important respects. In addition, radiation from the cosmic microwave background, CMB, which is considered strong evidence for the Big Bang Theory, was observed. Although the CMB provides a snapshot of the universe only 380,000 years after its birth, the anomalies in its distribution and intensity raise questions about the uniformity of a homogeneous universe from a single event. The search for answers continues with ongoing research projects and future space missions that aim to probe deeper into these cosmic mysteries. Projects like the European Space Agency's Euclid mission and future NASA missions beyond JWST aim to shed light on the early universe and its evolution over billions of years. In theoretical physics, efforts to reconcile quantum mechanics and general relativity still fail to produce a comprehensive framework that describes the conditions of the universe in its early stages. The singularity predicted by the Big Bang theory marks a break in our understanding of physics, where gravitational forces become infinitely strong and the classical laws cease to apply. As our technical capabilities evolve, so does our ability to challenge and improve existing theories of space. The advent of powerful telescopes, advanced computer simulations, and interdisciplinary collaboration offer unprecedented opportunities to test hypotheses and explore alternative explanations for observed phenomena. Beyond the scientific community, the implications of cosmological theories reverberate through philosophical and theological debates, questioning our place in the universe and our understanding of existence. The search for knowledge about the origin and nature of the cosmos is not only an academic endeavor, but also a goal of deep human meaning and understanding. In conclusion, although the Big Bang theory remains the dominant explanation for the origin and evolution of the universe, it faces controversy and challenges. Discoveries made with instruments such as the James Webb Space Telescope continue to push the boundaries of our knowledge, prompting a re-evaluation of fundamental assumptions and the search for alternative explanations for the mysteries of space. The constant dialogue between observation, theory, and interpretation underscores the dynamic nature of scientific inquiry and our shared journey to unravel the mysteries of the universe.